Hello and welcome to the fourth and final video of our math review. Now we're going to talk about some of the functional forms that we're most likely to encounter as we work through problems in the course. Now, functional forms is just the specific form of the utility or production functions that we're going to use. And some of them are actually pretty useful to know ex ante, to know before we actually work with the problems. It's useful to practice with them because this way problems later on are going to be simpler to solve as we can recognize the basics form of the solution from the practice problems we've done before. And in particular, the Cobb-Douglas function and the CES, the constant elasticity substitution function, are going to be very useful, and we're going to be encountering them often as we go along. Now, functional forms are characterized by parameters. We won't give specific value to these parameters. Instead, we want to know what happens to the solution if the parameter changes. Throughout the course, we're going to be denoting these parameters with Greek letters: alpha, beta, gamma, eta. Those are the ones in the screen. There are many others. I recommend that you check them out. It's really easy. But if you're having trouble with them, feel free when you solve a problem to replace them with normal letters that you know. So instead of alpha, you can use lowercase a. Instead of beta, you can use lowercase b. Instead of gamma, you can use lowercase g, so on and so forth. Sometimes this might be confusing, and that's why we will prefer to use Greek letters. But here is the important part. It is not the exact value. It's not if alpha is 0.5 of 0.6 or 0.3. That's not what matters. What matters is to understand the abstract role of alpha and what happens if, say, alpha is higher or lower. What happens to the decisions of agents? Okay, with that out of the way, let's talk a little bit about the Cobb-Douglas function. Here is an example where we have a utility that depends on consumption, and it also depends on labor. Now, the Cobb-Douglas is going to have a parameter. This parameter is going to be gamma, and it's giving us the relative weight in utility of more consumption versus more leisure. You can see that 1 minus gamma is going to be the power on leisure. That's going to be the importance, the relative importance of leisure in utility. Now, the Lagrangian is the same one we've seen before, and the first order conditions are the same ones we had before, just that now we're replacing the first order condition, the utility, the marginal utility of consumption, and the marginal utility of labor. We're replacing them directly with the derivatives of the utility function that I'm putting at the top. We already know how to interpret these conditions. We did that in the general case so that we don't have to do it for every functional form we encounter. That's because the discussion of how to interpret the first order condition is the same, actually, no matter which utility function we have. Now, depending on the utility function, we're going to have different properties for what does the marginal utility of consumption depends on. What does the marginal rate of substitution depends on? Is there a strong income effect or not? So that's what the exact form of the utility function is going to matter for, but not for the general interpretation of the first order conditions. All right? So, you can use this. You can then use the two conditions. We can replace lambda out of the condition for labor. We can then cancel out terms, and this actually gives us a value for consumption as a function of income. You can always be checking, do we have the right units? And so in this case, W is in units of consumption per units of labor. 1 minus L is in units of labor. They cancel nicely so that we get units of consumption on both sides. So we know we did it correctly. Then we can finish up by replacing back the constraint. So we know that consumption, which we now can express in terms of W and L, it's equal to our income. And then by replacing back, we can actually get a result for how much labor income do we want. That's kind of like what I show in the last line. It's a nice result of how much labor income do you want to have. All right. An important thing is that sometimes we can see problems that don't look like they are Cobb-Douglas problems, but they actually are just Cobb-Douglas in disguise. Here are two alternative utility functions. The first one just has gamma log of c plus 1 minus gamma log of 1 minus L. The second one has no gamma. Instead, it has log of c, and then it just has beta times log of 1 minus L. Turns out the solution to the problem under utility function u, the one we had before, let me go back, this one, the one at the top, or utility functions v or w are actually the same, because the first utility function gives rise to the second utility function. We just take logs at both sides. Then finally, if we just divide if we just divide everything by gamma and relabel beta as 1 minus gamma over gamma, we get exact same utility. Now, the reason here is the level, the units of the utility do not matter. What are they? They are utils. We don't know, like, it's 5 utils a lot, it's 7 utils a lot, is 1,000,000 utils a lot. It really doesn't matter, because the only thing that matters for us is which allocations give you more utility than others. It's the order. And so we can change the level of the utility by applying logs. That's what we're doing here to go from u to v, or by dividing by gamma. That's what we're doing to go from v to w. And that won't change the value of the solution. I invite you as an exercise to repeat the process we did here, but starting from values v and w for the utility. You're gonna find that the same solution, it's gonna come out. And this is really why we don't bother using specific value for the parameters, because at the end of the day, whatever specific value they have, it doesn't matter. What really matters is that we understand how those parameters affect the solution. Put it another way, if you go back here, you want to know what happens when gamma goes up. You can see that when gamma goes up, the value of your desired labor income goes up. And the way that happens is by working more. That should be very intuitive though, because when gamma goes up, the weight on consumption increases and the weight on leisure decreases. And so now you get higher benefit from consuming and a lower disutility from working. It is only optimal that in the solution, you want to work more and consume more, have less leisure in the process. So what matters really is the role of gamma here and not the specific value it has. Then we also encountered the Cobb-Douglas in production. I won't spend too much time in this one. You've seen it before a number of times in other courses. The first order condition is relatively easy to manipulate, and you're going to have these slides and you can work through the steps. If you have any questions about those steps, do reach out, and I'm going to be there in the office hours and we can work through them. And then finally, also one in which I'm not going to be spending too much time, we have the CES production function that in this case has two parameters: alpha, the relative share of each of the two inputs, capital and labor, and rho, which is going to give us the elasticity of substitution between inputs. And later on in the slide, I'm giving you just kind of the steps of how you can solve for the optimal value of labor given some value of capital. The important thing again is that you should be able to understand what happens here if W increases, if Z increases, if alpha increases. That's what's going to tell you something about the economics of the problem. Okay, I invite you to work through these examples and other examples in the sample problems that you're going to have for this module. With that, we finish our math review, and in our next video, we're going to go over chapter 11 of the Williamson's macroeconomics book. That's the chapter in which we're going to work in a two-period production economy in general equilibrium. So I'll see you then.